For decades, our ability to build faster computers, better phones, and smarter devices has relied heavily on a single, stubborn engineering challenge, making the electronic components inside them smaller. Right now, the entire computing industry relies on carving those components out of bulk silicon. Cleanrooms like this one are designed to protect delicate wafers as lasers and chemicals etch transistors directly into the material. But at ultra-small scales, the physics of bulk etching break down. This diagram illustrates what happens at the atomic level. When a structure is only a few atoms wide, a single microscopic defect, just one missing atom, causes the entire component to short out and fail. We cannot physically carve our way down to smaller and smaller electronics. To keep shrinking our technology, engineers have to abandon silicon etching altogether and build with completely new materials. A few years ago, carbon nanotubes were supposed to be the solution. We dominated the headlines as the ultimate successor to silicon. But carbon has a major flaw. When you shrink a carbon nanotube down to exactly 1 nanometer wide, engineers lose almost all control over its atomic structure during manufacturing. Because of that lack of control, microscopic variances randomly alter how the tubes behave. You might grow 2 carbon tubes that look identical, but one acts perfectly as a semiconductor, while the other acts like a metal, ruining the circuit. In quantum-scale engineering, building the tiniest components in the world holds zero value if you cannot guarantee exactly how they will behave once you turn the power on. That reliability issue is what led researchers at the University of Tokyo to investigate a totally different candidate, molybdenum disulfide, or MOS2. Their specific goal was to synthesize a single-walled MOS2 tube exactly 1 nanometer wide with a perfectly uniform atomic structure. The problem is that conventional chemical methods fail at this scale. They produce MOS2 tubes that are multi-walled, highly irregular, and usually wider than 10 nanometers, far too bulky for advanced electronics. MOS2 possesses the ideal electronic properties to replace silicon, but left to its own devices, it physically refuses to form stable, predictable structures at the 1 nanometer limit. To force the material into the right shape, the research team developed a mechanical solution called confined space synthesis. They started with a larger material. This diagram shows a boron matride nanotube, acting as a rigid outer mold. Researchers pump MOS2 precursor chemicals directly into the hollow tunnel, then expose the system to intense heat. Because the inner walls of the boron nitride mold are unyielding, the physical constraint crushes the chaotic MOS2 atoms, forcing them to lock into a perfect 1 nanoliter arrangement inside. This atomic precision allowed the team to measure the material's band gap, the specific energy threshold that dictates how well a semiconductor switches on and off. They confirmed that as the tube's diameter shrinks, this gap decreases in a perfectly predictable way, fulfilling a theoretical prediction made over 25 years ago. This method provides a reliable way to manufacture structures with atomic-level precision, ensuring every tube is identical and predictable. This exact structural consistency makes these nanotubes the primary candidates for gate-all-around transistors, which are slated to become the standard architecture in future computing. Notice the layout here in this 3D model. Because the semiconducting inner tube is totally encased by an insulating outer tube, engineers get 360-degree connectivity, allowing for total control over the electrical flow. There are still mandatory engineering hurdles to clear before you find one of these in your phone. Most importantly, researchers need to increase the length of these tubes from a few hundred nanometers up to at least 1 micrometer so they can actually integrate into practical circuits. We are years away from full commercialization, but the primary theoretical roadblock that was stopping us from making smaller transistors has now been cleared. The utility of this confined growth technique reaches into a wide range of materials. The same mold can be used to stabilize an entire class of non-carbon materials.